Hey guys, this is Mrs. Elliott. I still don't have much of a voice, so I apologize for the way I'm going to sound in this video. I'm recording these notes for you guys right now because my youngest son has the flu and my youngest child has pneumonia. So those are probably two good reasons for me to not be with you all today as I'm caring for them. All right, these are your lesson 5.A notes on factoring quadratics. And today we're going to focus on two things. We're going to focus on factoring a GCF and factoring a trinomial that has a leading coefficient of 1. I will get more into those in just a second. First up, what is a quadratic formula or a quadratic expression? And it is an algebraic expression that has the highest degree of 2. So anytime you see an x squared in your equation, and that is the highest degree, the number 2, we call this a quadratic equation. And right here, when you see ax squared plus bx plus c, this is called the standard form for a quadratic equation, where a, b, and c are all real numbers, and a cannot be 0, because if a were 0, as you can see here, then this term would not be here, and your highest exponent would then be 1 instead of 2. It wouldn't be quadratic. Okay, factoring. What is factoring? It's the process of finding what to multiply together to get an expression. We are familiar with factoring a number, say number 8. Number 8 is broken down into factors as 2 times 2 times 2. You might have created a factor tree at some point along your mathematical career. Okay, so the first example that we are going to factor is an example of factoring a GCF. Okay, and GCF stands for greatest common factor. I know you guys have heard this before. So when looking at the expression 2y plus 6, we know that both 2y and 6 have a common factor of 2. 2y is actually just 2 times y, and I know that looks like 2xy there, but we're saying 2 times y. And then we have 6, which is 2 times 3, okay? And if you look at both of those, they both have a 2, okay? So they have a common factor of 2. So the expression 2y plus 6 can be rewritten as 2 times the quantity y plus 3, okay? So once again, 2y plus 6 can be rewritten as 2 times the quantity y plus 3. Therefore, it has been factored into 2 and y plus 3. If you were looking at a factor tree with this expression, you would see it written like this. This is one of the branches, and y plus 3 is the other branch, okay? Okay, so like I said, what the above did was factor out the greatest common factor. So let's try a few examples using two different methods. So the first method is with factor trees, and this is very elementary to do this method, but if you like this method, then go for it. It doesn't matter what you're doing or what the person next to you is doing. Is what works for you. Okay, so as you can see, as I was blabbing, I just broke down each of these terms into all of their possible factors. So let me do some highlighting here. Right here, 5x squared broke down into 5 times x, and 10x broke down into 5 times 2 times x, okay? And so with that, I can now look and see what were the common factors. They're right there in front of me. Okay, so I'm going to circle the 5 and circle the 5. They both had a 5. Now I'm going to circle an x and then circle another x. They both have an x in common. And then I'm going to look and I'm going to see an x and I'm going to see a 2, and I am definitely out of things that they have in common. So the GCF was 5x. It was what both terms had in common. Now inside parentheses, I'm going to write what's left over. There was an x left in the first term. There is a plus sign that connected the two, and then there was a 2 to bring down. And that is the answer. A second method that we can use is called the box method. Okay, let me highlight that back there. I didn't. It's called the box method, and the box method, it basically shows us the area model. I really love this way of representing an expression because it can be transferred into more difficult problems and very helpful when we get to them. All right, so I have just separated each term into a different box, and then on the outside of this box, I'm going to pull out what I know to be the greatest common factor. And looking at negative 4x squared and 24, there's not an x in both terms, so we can't factor out any x's. And negative 4 and 24, my knowledge of my multiplication facts, I know that the greatest common factor is 4. So I'm going to pull out a 4. And when I do so, up top here, I'm going to write what's left over. Now, let me tell you this. When you are factoring out the greatest common factor, it's always a good idea to factor out that negative. Now, you don't have to, but I know that we can all agree that this one had a negative, and if we factor a negative out of this one, we can assume that we would have to multiply it by a negative to get back to positive 24, because a negative times a negative is a positive. And let me show you what I'm talking about by writing the rest of the problem up here. I'm going to put an x squared here because I know that when I multiply those two together, I would get back to negative 4x squared. And then now I'm going to ask myself right here, what times negative 4 would give me 24? And I know that that's negative 6. Negative 6 times negative 4 would give me 24. So now I'm going to write it out like this. And the reason I pulled out that negative right there was to keep my x squared term positive. It's just kind of the right thing to do when factoring trinomials, is to keep that x squared positive. Why? Because we might end up in a situation where we're just graphing what's inside these parentheses, and it makes life much easier if at all possible, especially if we're having to factor even more inside of those parentheses in future lessons, okay? Now, it's time for a you-try. If you guys want to pause the video, try examples 3 and 4, and then play the video back and see if you get the right answer. I think that'd be a smart idea. All right, so I'm going to go ahead and work them out. And on this particular one, I am going to use the tree method. So this is 3 times 2 times 2. And then I've got 2 x's. And then here I've got 3 times 3, and I've got 1x. So I'm going to circle what they both have in common. They both have a 3 in common, and they both have an x in common, and that's actually it. So the greatest common factor is 3x. And then what's left inside? There is 2 2's and an x. So 2 times 2, putting that back together, is 4x. And then over here, the only thing left was a 3. All right, so there's that one. And then the next one, I will do the box method again, and I'm going to place 15x squared here. I'm going to place 12x there. The greatest common factor going across here is 3, and they both have at least one x in common. Now above it, I'm going to write what times 3x would get me back to 15x squared. Well, 5 times 3 would get me to 15, and x times x would get me to x squared. And then here, what times 3x would get me to 12x? Well, a 4 would get me there. 4 times 3x is 12x. So my answer here is 3x times the quantity 5x plus 4. Okay? Now, factoring trinomials. So when we factor trinomials, it is an expression with 3 terms. So tri here meaning 3 terms. Okay? And so some unique trinomials can be factored into 2 binomials. Bi here meaning 2. So we have a quadratic expression here that can be factored into this. So here you have your 3 terms, 1, 2, 3, factored into 1, 2, 1, 2. Okay? So a trinomial factored into 2 binomials. And it did say the word unique up here because, sorry if that timed out. It did say the word unique right there because, and this can't be done with every trinomial. So often you might say cannot be factored. Now don't get into the habit, if you simply can't figure out how to factor it, to write cannot be factored. Really only write that if it genuinely cannot be factored. Okay? I'm just going to prove to you that this equals this very quickly using what's called left to right distribution, also known as FOIL. So if I have this expression times this expression, my first term times my first term, that's the f of FOIL, is x squared. My outside 2 terms right here, x times 3 is 3x. My inside 2 terms here is 2x. and then my outside two terms, or sorry, my last two terms multiplied by each other equals 6. So I get x squared plus 5x plus 6. And so now I have shown you how these two binomials multiplied together do in fact equal this trinomial. Notice the connection of the above terms. Okay, so let's reference the connection. When you look at this last number, okay, we know that 2 times 3 equaled that last number. Why? Because that's where we did our last. Okay, now notice what happened when we did the outer and the inner. The outer and the inner are written right here, and those two terms end up being added together. Okay, and so we can go back here and say that 2 plus 3 equaled 5. Well, it turns out that's a pattern in every trinomial where you have a leading coefficient of 1, this guy right here at the beginning. If you don't see a number at the beginning, this trick will work every single time. Okay, so if you didn't catch that, let's look at this example right below it. Okay, so here, the last number is a 6, and that middle number is a 7. So just a minute ago, we had two numbers that multiplied to equal this last number, and they actually both added to equal that middle number. Okay, just a minute ago, you had 2 times 3 was 6, you had 2 plus 3 was 5. So down here, let's do the same trick. Think of two numbers that'll multiply to equal 6 that will also add to equal 7. Well, we know it's not going to be 2 and 3. We just did that a second ago. Yes, it does equal 6, but when you add those together, it does not equal 7. Well, what other factors multiply to equal 6? How about 6 and 1? Yes, those two multiply to equal 6, and guess what? They add to equal 7. So we can quickly take our answer, put an x here, put an x here, because you know that x times x will give you that x squared that you want. And then if I place a 1 here and a 6 here, 1 times 6 will give me that 6 that I need. And when I do this times this, I get 1x. X times 6, I get 6x. I add those together, I would get my 7x. This is the factored form of this trinomial. It is a quick trick. It works every time. Let's go to the next page. All right. You try problems. You can pause the video now and give this a shot. You can go ahead and watch me. It's up to you. So I need two numbers that'll multiply to give me 12 and add to give me 8. And this will start being very quick for you. You can do two things. You can simply just, boom, think of the answer. Or if you're having trouble, you can list out all the factors of 12. 1 and 12, 2 and 6, 3 and 4. Those will all multiply to give me 12. And then identify the two that actually add to give you 8. Right there in front of me, I've got 2 and 6. I know those will add to give me 8. So boom, x plus 2, x plus 6. The order in which you place these two numbers is not important. I'm simply looking for 2 and 6 to be inside the parentheses, both with an x. Okay? Next. Excuse me. Two numbers that'll multiply to give me 25 and add to give me 10. You can list out your factors, 1 and 25, 5 and 5. Well, guess which two add to give you 10? You guessed it, 5 and 5. So x plus 5 and x plus 5. This can be simplified even further to x plus 5 squared, because anything multiplied by itself is essentially being squared. Okay? The above trinomial examples were all positive terms, so therefore the answer had all positive factors. So when you see an all positive problem, you will have an all positive answer. Very easy. So what happens if negative terms are involved? Well, first up, if you see the last term is positive, okay, last term is positive, you know that two numbers had to be multiplied to give you a positive, okay? But then you look over and you see this negative, and that throws you off, because you know that the two numbers also must add to give you that middle term. Well, the only time that you can ever have two numbers multiply to give you a positive but add to give you a negative is if they're both negative, okay? If they're both negative. And I hope that makes sense, because a negative plus a negative does in fact still give us a negative, but a negative times a negative gives us a positive, okay? So let's look at numbers 3 and 5 first, okay? So let's think about the factors of 9 that are both negative, -1 and -9, -3 and -3. Which of those would add to give us -6? Well, -3 and -3. So my answer is x minus 3, x minus 3. And yes, we can simplify that and write it as x minus 3 squared. On this next one, factors of 12, negative 1 and negative 12, negative 2 and negative 6, and negative 3 and negative 4. If you ever find the factors before listing them all out, go ahead and circle it. Like you guys probably saw that it was negative 1 and negative 12 before I listed out the others. We'll go for it. So therefore, we know the answer is x minus 1 and x minus 12. All right, what if they're both, what if the last term is negative? So here we see they're both negative, but here we see that this one's negative and this one's positive. So the key here is that that final term is negative. If that final term is negative, we know that a negative has been multiplied by a positive. So we know that our factors are going to be one negative, one positive. So I'm going to list out the factors of 20, but flip-flopping the signs of the factors. Your list could be a little longer here. Negative 1 and positive 20, or positive 1 and negative 20, negative 2 and positive 10, or positive 2 and negative 10. You could also have positive 4 and negative 5, or negative 4 and positive 5. So here are your factors of 20, and we want two numbers that will multiply to give us negative 20, but also add to give us negative 1, okay? Add to give us negative 1. And I go through my list, and the two that add to give us negative 1 are 4 and negative 5. So we have x plus 4, x minus 5 is our answer. This next one, negative 10, we have negative 1 and positive 10, positive 1 and negative 10. We have negative 2 and positive 5, positive 2 and negative 5. And the two that actually add to give us positive 3 are right here. So we've got x minus 2 and x plus 5. Okay? Now I'm going to give you one more example that you don't see on here before you start to practice your classwork. Okay? And the last example that I'm going to give you, that I'm just going to write in a different color and squeeze in here. What if you had, let's see, 2 times the quantity, or I shouldn't say 2 times the quantity, I'm so sorry. What if I had 2x squared plus, let's see, plus 16x plus, I'm trying to come up with this on the fly. Give me just 1 second. 32. There we go. So sorry about that pause in there. Hopefully I didn't bore you all too much. All right, 2x squared plus 16x plus 32. Obviously, our leading coefficient is not 1, so we're not going to do the trick that we were just doing. But I look and I think, hey, 2, 16, 32, it has a GCF. So I'm going to factor out that GCF. The GCF here that they all have in common is the number 2. And after I factor it out, I'm left with an x squared, I'm left with an 8x, and I'm left with 16. And now I look at the inside and realize it can be factored. How do I know it can be factored? Well, I'm going to try it out. I'm going to list out the factors of 16 and see. 1 and 16, 2 and 8, 4 and 4. Oh, wait a second. 4 plus 4 equals 8. So I can factor this, and it factors into 2 still there on the outside, x plus 4, x plus 4. And then, yes, I can simplify that even further, still having the 2 on the outside, but x plus 4 squared, okay? So if you do see a number in the front, okay, which you don't see on examples 1 through 8, but on your worksheet/homework, if you see it, factor out that GCF and then attempt to factor what's on the inside. I hope this helps, and I really hope to be back on Tuesday. If you do have any questions, feel free to email me, and I will answer any questions as quickly as I can. All right, thanks, guys.